All right. Thank you. One second. All right, well, 41 more minutes since people are still coming in, and then we'll get started. Think let's get going. Welcome to the AstroAI lunch talks. Today we have two speakers as usual, Sina and He. And it is my pleasure to first introduce Sina Taamoli from UC Riverside. Sina is a grad student there working on studying mass and environmental effects on star formations of galaxies at intermediate redshifts. And he's going to be telling us today about his ideas on applying machine learning to this interesting problem. So, Sina, the floor is yours. Please remember to interrupt with questions anytime, and you have the first half of the hour.
Thank you for the introduction. Hello, everyone. My name is Sina Taamoli. I'm a fifth year graduate student at UC Riverside. First of all, thanks for having me here. I'm super excited to present my works and discuss my ideas about the astronomical side of my research and the AI applications in that. On the astronomical side, I'm mainly focused on environmental dependence of galaxy properties and extraction of cosmic web components. And recently, in the 1.5 year, since the 1.5 year ago, I started to think about AI applications in my work. And today I'm going to be presenting those ideas and some preliminary results and other works in my primary astronomical research in this presentation. Before I dive into my presentation, I wanted to mention a quick note. As you may have noticed, that the title of the talk is totally different than what was initially announced. And the reason is, as I was developing my presentation, I added more and more AI-related topics to my presentation to make a better fit for this talk. And I got too far from the initially announced title. So I had to change it, and we didn't have time to make another announcement. So I apologize for that, and I hope it adds extra layers of excitement instead of making more confusion. Okay, let's start with the astronomical side of my research. I started working on somehow traditional stuff in astronomy and for the first half of my PhD, and then I tried to find ML-powered solutions for the questions and the problems that I faced. And for that, I'm going to be present in the first part of my presentation. I'm going to be talking about identification of large-scale structures in galaxy surveys, environmental properties of galaxies, and the high-dimensional parameter space that we have in these studies, and another problem that we have in analyzing large galaxy surveys to answer these science questions. And for the rest of my talk, I will be focused on the ideas that I have to tackle these questions. When I started my PhD, Cosmos 2020 catalog was out, and I started with reconstruction of the density maps using Cosmos 2020 data in 135 redshift slices spanning redshift 0.4 to 6 with constant comoving widths of 35 megaparsecs and using kernel density estimation. We constructed these density maps throughout this whole redshift range, and we created a density catalog for 210,000 galaxies, again, across this redshift range. It was important to me, as this is the home for many X-ray astronomers, because we have fundamental questions that we have in terms of the distribution of different populations of galaxies across the cosmic field. For example, the question of are X-ray groups concentrated in high-density environments, and the same question can go for AGN, for example. And as an example here, as we can see here, we can see that some X-ray groups reside, in fact, in high-density environments. And we needed to first reconstruct the density maps and cross-match our density catalogs with X-ray groups. And some preliminary results from an ongoing research on this topic is shown here. We can see that the X-ray groups are generally reside or concentrated in higher density environments. So we are working on this. And other questions, I just briefly mentioned the questions that we had under this topic, and then we'll jump onto the AI applications. Another question was how are galaxies distributed in various components of the cosmic web, and what galaxy populations trace the largest scale structures such as filaments, or in a more general sense, what are the observational tracers of those largest scale structures? For that, I used Hessian matrix analysis, which is basically the analysis on the second derivatives of the second derivative field of the density field, and expanded my initial analysis on the density fields. Here on this panel, we can see the spatial distribution of sources within the cosmos field, and they are colored by the probability of each galaxy being in a redshift slice based on the photo-Z's and redshift PDFs from Cosmos 2020 calendar. And here we can see the reconstructed density maps. And here, these two plots on in the bottom are the results of that Hessian matrix analysis. We assign cluster and signal and filament signal to each point within the field. And now we have three environmental features. We have the environmental density, we have the cluster signal for all the galaxies within the field across this whole redshift range from 0.4 to 4, and we have filament signal for each point. I'm adding more dimensions to the problem of environmental dependence of galaxy properties. In addition to that, we investigated the role of galaxies' environments in their star formation activity. This is the result, and the only thing that I want to mention here is that we can see different regimes in the relation between star formation. The relation between star formation activity and environmental density. At lower redshifts, we see an anti-correlation between the environmental density and star formation activity at intermediate redshifts. By intermediate redshifts, I mean redshift between 1 and 2. We see almost no correlation within the levels of within the uncertainty levels. And at higher redshifts, we see a positive correlation between environmental dependence, environmental density, and star formation activity. And there's a lot of debate about these high redshift regimes. And to make it even more complex, we try to involve the role of mass in this scene. And here we can see the environmental density as a function of stellar mass and colored by star formation activity. And these circles represent the scatter of the data around the mean values. So we can see how complex is the scene. And this is where I want to conclude the astronomical part of my talk. I just wanted to mention the general astronomical questions that I tried to tackle with traditional methods or conventional methods in the astronomical side of my research. And the results can be found in these works, the results of analysis on the environmental dependence of galaxy property. And as I mentioned in the last slide, we have a high dimensional parameter space. We have at least 3 environmental feature, environmental density, cluster signal, and filament signal for each galaxy within that Calibrated generate. And we have internal properties or physical properties that are acidity fitting extracted. We have stellar mass, we have star formation rate, and other. We have colors, and in Cosmos data we have more than we have observations in more than 40 bands. So we have too many dimensions, and in the we have upcoming wide area surveys such as Roman, such as Euclid, and Euclid is the first data is out. But in these surveys, we have missing bands for acidity fittings and extraction of physical properties. So missing band is another problem that I'm going to address in the second half.
Sorry for interrupting. Before you move on to the AI part, can you tell us, do you have a current interpretation of that change in the trend between star formation and density for different redshifts? Is there an interpretation for that?
Yeah. It seems that let me go back to here. From here, it seems that the main driving parameter in star formation activity is at least up to redshift 2 is mass instead of environment. At lower redshift, we can see that for very massive galaxies, star formation rate drops significantly, but at intermediate mass regimes, in the very extreme environment, the star formation drops here. So it seems that environmental quenching processes such as galaxy mergers and galaxy-galaxy interactions and tidal effects quench the star formation activity at lower redshifts. But the role is different at higher redshift. It seems that because of the higher availability of cold gas at higher redshifts, at least it's our interpretation, because of the higher cold gas, which fuels the star formation activity at the early stages of galaxy evolution, the environmental dependence of star formation activity is reversed at high redshift. So that's our interpretation, that the role of environment shifts between high redshifts and intermediate and lower redshift regimes. And the transitional epoch is between redshift 1 and 2. And recently we have other studies working on this and getting the same results from both simulations and observations, getting spectroscopic observations, getting the same result, the reversal of environment star formation activity at high redshifts. But there's a lot of debate around it. So I'm going to be talking about missing band imputation, statistical learning techniques, and particularly dimensional reduction methods that we are currently working on to tackle the questions that could be answered with this high dimensional parameter space. So the big questions, the astronomical questions as a summary is which galaxy populations, these galaxy populations could be star forming, quiescent, live and break galaxies, X-ray groups, AGNs, etc., reside in low or high density environments. That's a question coming from my astronomical background. What are the observational tracers of galaxies in high density environments? It's important because if we could find observational tracers of these high density environments, it's generally expensive to estimate the environmental density of galaxies. We need to have a deep observation over a wide area to be able to extract environmental features. Instead, if we could find observational tracers, we'll be able to perform follow-up observations in the future, based on just some observational measurements. And the last question is how are physical properties of galaxies, such as star formation and stellar mass, related to their environmental properties? And the environmental properties are generally density and shape here. And finally, how can ML techniques unveil the underlying patterns in this complex high-dimensional parameter space? And how can we address missing band problem with ML techniques? So about 2 years ago, we started working on the problem of classification of galaxy populations with different machine learning techniques, a comparative study of different machine learning techniques in this decision problem in the most general sense. Selecting or classifying galaxies from observational data in photometric catalogs is basically a decision problem. We have conventional, traditional methods to make that classification, and there are a lot of machine learning techniques that are developed for the problem of classification. This is a general problem, but here in this study, we, as an example, we just focused on high redshift massive quiescent galaxies in our sample. And the sample that we were focused on was the photometric catalog from Woods S field in 5 out of 5 candles fields. And we needed a ground truth for our classification problem. And for the ground truth, we used the light cones generated from the Santa Cruz semi-analytic models that are basically generated based on the dark matter simulations and basically generating mock simulational observational catalogs for the same field. We used the light cones that were generated for the candles field, and we tried to make a mock catalog of that generated light cones, similar to Woods S observations that we had. So that basically forms our ground truth for applying and comparing different ML techniques. So in the next few slides, I'll be focused on missing band imputation method that we applied, the comparison of different ML techniques, and among these ML techniques, I will be more focused on dimension to reduction techniques, as I'll go back to it at the end of my talk. So the missing band problem is important because we have observatories that are retired, and we won't have observations in those bands in the upcoming surveys. So we need to somehow estimate the missing the missing values in those missing bands. There are very simple methods to estimate the missing values, missing band observations, such as just interpolation of adjacent bands. But here we used a method named as multivariate imputation by chained equations. We had the mock catalog from semi-analytical models with all the information, all the labels are known. We artificially removed some of the bands from that catalog. We had 12 bands similar to candles fields, and we tried to estimate those missing bands based on the available observational data in other bands. So here, the method is estimating missing magnitudes as a function of non-missing magnitudes for each band, and measure the performance of our estimators and classifiers for the original data without any missing band, and the data set with artificially missing bands replaced by our estimated values. This is the result for missing band estimation for different bands. Here on the vertical axis, we have the estimated values, and on the horizontal axis, we have true magnitudes, which come from the mock catalog that we started with. And we can see the performance of our missing band estimator or missing band imputation method in these plots. Talking about the classifiers, we were looking for the optimal classifier, and we wanted to compare the effectiveness of different statistical learning algorithms in identifying a specific population of galaxies. And as I mentioned earlier, we were focused on high redshift massive quiescent galaxies. The physical selection criteria for these galaxies is outlined here. So we have the mock catalog with all the known information about all the galaxies, and we can perform the selection criteria to pick the true high redshift quiescent massive galaxies. And the next problem was to try to estimate those populations with a function like h here, taking the feature vector xg for each galaxy, and the feature vector is all the observational data in different bands for each galaxy. So the problem of classification is to somehow train and make an approximation for this function h. And if the output is 1, it's the galaxy that is a member of quiescent population, otherwise it's 0, or it could be a continuous classification. These are different techniques that we use, and we are testing and comparing in our work from Bayesian posterior expected loss and approximating the true classification function. But I will be, in the next few slides, I will be more focused on dimensionality reduction techniques, which is in this work, supervised principal component analysis, T-distributed stochastic neighbor embedding, and uniform manifold approximation and projected, or simply UMAP. Dimensionality reduction techniques are generally used to approximate the manifold on the higher dimensional space on which the data points reside, and trying it's trying to make a transformation from that high dimensional manifold to a lower dimensional manifold, conserving the relations or similarities between the galaxies in the higher dimensional space. So that's the general idea of dimensionality reduction methods. And the lower dimensional representations can be used to identify any class of galaxies, and it's shown that it can be used to extract physical properties. There are many works that use dimensionality reduction techniques to, for example, distinguish star-forming dusty galaxies from quiescent galaxies, and extraction of physical properties. For classification, we use k-nearest neighbor classifier in this part in dimensionality reduction techniques. And this is the result for supervised principal component analysis transformation. As we can see here, in these two principal component axes, we have all the galaxies, all the non-high-Z quiescent galaxies shown in blue. We have the high-Z quiescent massive galaxies shown in red. And as we can see here, this method aims to find a transformation in which the statistical dependence of properties and those transformed quantities are maximal. So as we can see here, we can group these massive, high-redshift massive quiescent galaxies here. And if we focus on these areas, we can see there are contaminants from non-high-Z quiescent galaxies. But still, we can see that in both testing projection and training projection, we have almost all of these high-redshift massive quiescent galaxies grouped together in this two-dimensional space. And we've also tested TSNE transformation and UMAP transformation. These are basically two almost similar methods, but different in details. UMAP transformation is doing better in conserving the global relations in the data in the higher dimensional space when transforming the data in lower dimensions. And TSNE works better in local relations in the data set. So here we can see the representation of our data sets in the lower dimensional space. As we can see here, if we turn on the redshift in this reduced dimension space, we can see that the high redshift galaxies are, for example, grouped together at these points. Or if we turn on the stellar mass, we can see that we can identify more massive galaxies at this part of the this map. And the same goes for star formation activity. And we can see some patterns in the results of UMAP as well. These are semi-finalized results from our work. And we try to make the classification using k-nearest neighbor method, and we try to assign a probability to each galaxy being a member of that population of massive quiescent galaxies, high redshift massive quiescent galaxies, based on the fraction of these k-neighbors. And using 5-fold cross-validation on the validation set, we ended up with k equal to with k equal to 50 neighbors for our sample. That's just technical details. And here we can see the outcome of basically the comparison between these methods and the true classification and ACD fitting based classifications on both incomplete data and complete data. Complete data has all the values even in those missing bands, and incomplete data is the data with missing values. And here it's the true classification. So in fact, we're comparing the performance of all these models with the true classification. And these are the performance of dimensionality reduction techniques that I was focused on and in the previous slide. And the performance of these techniques are also presented here in the purity completeness diagram and RC curves. So we can see that at different regimes, different algorithms have various have very different performances, and it's generally the performance of these algorithms generally depends on the computational cost of our job, whether we're able to, for example, run ACD fittings, or we want to apply these dimensional reduction techniques. And the other important thing is that ACD fitting techniques generally perform better in I just forgot that. It generally performs better than compared to dimensional reduction techniques at higher redshifts. So as a summary, we are in the process of comparing all these different methods with traditional and conventional methods, such as ACD fitting. And in the next step, getting back to the original problem that I stated at the beginning of my talk, that high dimensional space of environmental features and observational features. We are going to, as a next step, we are going to apply these dimensional reduction techniques. We are working on self-organizing maps currently to our data sets, including the environmental features, to see if there is any observational tracers of galaxy environments, and to see if specific galaxy populations, such as X-rays or agent, are populated in specific environmental regions in the environment space, and to see what are the underlying patterns between internal factors such as stellar mass and star formation activity, and the environmental factors such as the environmental density and the shape of the environments that cluster and filamenting. This is the topic of our current ongoing research. Thank you for attending this presentation, and I'll be happy to take your questions if we have time.
Thank you, Sina. Thank you for an answer. Maybe I would mention, I would say, it looks like your dimensionality reduction, purely dimensionality reduction, is not quite capturing, the same level of complexity that the neural network is. Maybe the neural network is learning some features that are more relevant for this classification problem. Have we considered maybe doing further classification, first running the neural network and using the features that the neural network learns, and then apply dimensionality reduction to those features instead?
That performance comparison was based on this specific topic, selecting with this specific population of galaxies. We are first going to try self-organizing maps as well on the environments catalog that we generated, and then that would be another topic that would be another thing that we need to do to run neural networks to find the underlying pattern. And we also, in identifying large-scale structures such as filamentary structures, I think we have a lot of comparative studies of AI-powered techniques. But I think it's the time to conduct another comparative study of application of different pattern recognition algorithms in identifying large-scale structures. That's another thing that I don't think that I have time to during my but I plan to.
All right, well, thanks very much. Ready to move on to the next talk. Thanks very much again. And for the second talk, we have Heya. He is a grad student at Princeton, and he works on simulation-based inference for cosmological simulations. He's going to introduce a new method for SBI, in particular one that uses some low fidelity simulations for training and then calibrates with higher fidelity simulations and uses this to extract and get posteriors for relevant cosmological parameters. So, assuming that you're all set, the floor is yours. Thanks very much.
So do I need to turn on this?
Yeah, I think it has a button right there, so you need to. Yep.
Okay. Okay, so my name is He Jia. I'm a final year grad student at Princeton, and I actually work on a number of different topics. I also work on black holes. For that, I'm studying how to measure the spin of the black hole from photo arrays. Well, for cosmology, I'm working on the inference of the large-scale structural data. And today, I want to advocate a new framework for the simulation-based inference. So although I will demonstrate this for a specific cosmology problem, I would say this method can be applied to any SBI problem where you find that the simulations are too expensive to run. So this is not really limited to cosmology. It can be applied to any problem. Okay, so the cosmology problem I want to solve is that I want to infer the cosmological parameters from this kind of maps. But to get this kind of maps, we need to run the simulations. And currently, the surveys are getting to larger and larger volumes and also down to small scales. For example, if we want to simulate the full scale electron up to redshift of 2, we need to run a 10 gigapascal box. So this is too expensive if we want to run simulations at this box size. If you want to run this high-fidelity particle or hydrodynamic simulations for the SBI analysis. So there are some workarounds for this issue. So some people propose that we can just stack in a lot of small box simulations to get this large volume. But the problem is that if you do this by definition, you are not getting the large scale modes correct. So you need to account for the so-called supersample effects, which are not so easy to model. And alternatively, some people are using this approximate simulators, such as this particle mass measures or some emulators to run the simulation. But this will not be accurately enough at small scale. So you will see some bias if you do this. And so I want to propose a framework where we can solve this problem by first training this here NQE means Neural Quantile Estimation. So this is a new simulation-based inference method that I will give a brief interview in a few minutes. And so this can be trained on a lot of approximate simulations that you can easily get 10,000 of them. And after the training, you can calibrate it with just 100 high-fidelity simulations. And after the calibration, the posterior is guaranteed to be unbiased on these high-fidelity simulations, regardless of the accuracy of your approximate simulation. But it's just that if your approximate simulation is accurate, the posterior or the calibrated posterior will be close to optimal. You will have almost all the constraining power. And in this work, I'm using this particle mass simulations for this approximate simulations, and I'm using this high resolution particle simulations for this high fidelity simulations. But as I just
Sorry, finish your thought.
as I just emphasized, this is not really limited to cosmology. This can be applied to any problem where you have this health of high fidelity and approximate simulations.
Yeah, so can you explain a little bit what the approximate simulations are?
So this is just any faster approximation to this high fidelity simulation. So in this setup, I'm assuming that this high fidelity simulation is really seamless what's happening in our universe. And this is any approximation to it that is faster to run, but not so accurate at some, for example, at small scales.
Okay, but you do those approximations? How do you get those approximations? Is there
so for this
transfer function correction?
For this particular problem, I mean, so this particle mass simulation is just another way to do this kind of unbody simulation, but it will not include the particle interaction at a very small scale, so it's not very accurate at small scale. That is faster to run. And for this transfer function correction, I will get back to this later, but this just means that I will, as a leading term correction, I will just correct the Hall spectrum of that. So I will get back to this later. Yeah. Okay, I will move on if there are no more questions. So I will first give you an interview of this neural quantile estimation. So this is basically a new simulation-based inference method, and it will do the inference by first. So here, theta means the model parameters that we want to learn, and in this case, it's the omega and sigma 8, the cosmological parameters, and x is the data, and in this case, it's the cosmological maps. So I will first do this autoregressive decomposition to decompose this into a lot of one-dimensional conditional distribution. And for each of them, I will use a neural network to learn the quantiles, to learn the, for example, 5%, 10%, 15% quantiles of these one-dimensional conditional distributions. So to do this is you just need a weighted L1 loss, because as you might already know, if you do regression with L2 loss, you get a mean. If you do regression with L1, you get a median. But if you add some weights to the L1 loss, you will get the arbitrary, like 5%, 10% quantiles from of this distribution. So
sorry for interrupting again.
Sure.
So sorry for my ignorance, but when you say the data in this case is cosmological maps, what do you actually mean? Is this, large scale structure of baryonic measurements? Is this dark matter maps? Is this
for example,
of galaxies? Where is it?
For example, the overall density map of the galaxies, the overall density
Okay.
for the spectroscopic servers,
Okay.
or maybe all the convergence maps for the wavelengths, yeah, something like that.
Thanks.
Yes, so as I said, for this, I will do this autoregressive decomposition to learn the quantiles for each one-dimensional conditional distribution. And once I get, for example, the 20 individual quantiles of this one-dimensional distribution, I will do the interpolation to reconstruct the full distribution. So in this plot, I'm just showing you the reconstruction. So the green one is the truth, and the red one is the reconstructed distribution, one-dimensional distribution from I think roughly 15 quantiles. And so the blue one is just a comparison of a larger interpolation scheme. I just want to say that with the blue one, I have some artifacts here, but with the red one, there's almost no artifacts. So I can perfectly reconstruct this one-dimensional distribution from the individual quantiles. And as I said, I will use the neural network to estimate the individual quantiles of each of them, and then interpret them to get the full distribution. Okay, so the good thing of this NQE method over the other existing simulation-based inference method is that, this can be easily calibrated as follows. So as I said, we want to calibrate this with approximately 100 high-fidelity simulations. So I will do this two-stage calibration. So in the first step, so as I said, the output of the neural network is like the 5%, 10% quantiles of the one-dimensional conditional distribution. I will ask the question whether this is really the 5% on the calibration data set, which means that whether I really have 5% on the left and 95% on the right. And if this is not true, I will add a shift to correct this quantile. So effectively, I'm averaging over the area. I'm averaging the area. I'm averaging the area over the calibration data set for all these quantiles. So this is the first step. And after this, I mean the posterior is usually not that fast. But if you are a serious statistician, you will find that the empirical coverage is still not a diagonal. So I will then apply a second important sampling step to really make sure that. So for this, I will check whether, for example, I really have alpha percent of the truth within the alpha percent of the parallel regions. And if this is not true, I will add important sampling weight to each of these samples based on its probability density at the truth. So to make sure that you really have a diagonal empirical coverage. Is that a question?
Actually, I have a question. Thanks. So if you only had one parameter theta, this would make perfect sense. You have many parameters. So for example, you need the conditional probability of omega matter given sigma 8 and the data or whatever. But then that means you need to have enough of your simulations in the same range of sigma 8 that you're interested in for that conditional probability that you're testing. So it seems like you would need a lot more than 100 simulations. Why is it okay to have only a small number of simulations to calibrate with?
Oh, because I mean, so for this first step, so I'm calibrating each dimension individually. So because I'm for this, all I need to do is just to evaluate the 5% quantile on the one-dimensional conditional quantile of your distribution. So this does not really depend on the dimensionality.
But no, I think it does, because if you have a distribution of theta 1 and it's conditional on theta 2, you need to get that distribution of theta 1 correct for all the values of theta 2.
But I mean, this is, you want to check on average whether the quantile of theta 2 is correct. So and for that, so because I mean technically, so for theta 2, technically theta 1 you can just think of it as just one actual dimension of the data. So these are joined as the input of the network for theta 2.
Okay, let me think about that.
Oh, we'll have that later. Yeah, okay, as I said, so this is a two-stage calibration, and I would say this first step, this one, I only know how to do this for NQE, I don't know how to do this for the other SVM methods, because the other method will not give you the content. Well, the second step, this in principle can be applied to any simulation-based inference method. But now I will show that, I mean, if you only do one of them, if you only do either one of them, you will not always get a perfect coverage. So you really need both of them. And as I said, if you only do the step 1, the coverage is not guaranteed to be diagonal. And on the other hand, if you only do step 2, so this will not always be optimal, because I mean, if you by doing the implicit sampling, so the implicit sampling weights are only dependent on the probability density at the truth. So basically, this cannot modify the iso density surface of the posterior. So here I have a toy example. Let's say the red one is the truth, and the purple one is the uncalibrated bias posterior. And if you only do the implicit sampling calibration to this, in principle you can get a diagonal coverage or properly calibrated posterior, but you will get something like the blue one, you will get a ring, because this cannot really modify the isodensity surface of this purple distribution. So it will somehow downweight the samples at the center and upweight the samples at the on the edge. So you will get something like the blue. But on the other hand, if you apply the shift, you will recover the perfect posterior as the green one. So the takeaway message from this is that you really need both steps to do the calibration to really do an optimal and efficient calibration. Okay, so let's get back to cosmology problem. So the basic setup is that I'm doing this 1 gigaparsec bus with 512 field particles, and for each of them, I'm getting 24 two-dimensional projected dark matter density maps like this. So, and for the high-fidelity simulators, I'm using the paleo simulators from the Quixote. So this is a set of unbody simulations run by Paco and CCA, and this is kind of the largest one of this kind at this point for the scale analysis. And on the other hand, we also have I'm using this fast PM simulation for the approximate simulations, and so this is roughly, each of this is roughly 100 times faster than the particle simulations. And as I said, I'm applying a transfer function correction to this particle mesh simulations, which just basically means that I will run 50 simulations with the same initial collision, and I will do this with particle and also particle mesh, and then I will use Gaussian process to learn the ratio of the Hall spectrum between these two, and then I will apply this transfer function correction to my particle mesh simulations, such that as you will see after you apply this correction, you will get the correct Hall spectrum, but this will do nothing for the cross correlation. I'm also comparing a few different data compression schemes. So the first two, these are the predefined summary statistics. These are the Hall spectrum and the scalar transform. And on the other hand, I'm also doing a convolutional neural network. For this, I'm using a 42-layer set. And here I do have a convergence test which justifies why I need 42 layers for this work. And so for each of them, I'm using a 10-layer MLP to estimate the quantile. So now let me show you the results. So here I want to give you some idea of what the calibration is actually doing. So on the left-hand side, this particle mesh plus transfer function correction, and this is the uncalibrated posterior. And as you can see, the posterior is failed because at this point the truth is here. But on the other hand, if you do the correction with just 100 simulations, you will remove the bells, as in this panel. And on the right hand side, these are all calibrated posterior, so they are not bells, but they are trained with different simulations. So this is with the parameter with the correction, and this is using 400 particle as a comparison, because this will be this will have a similar cost as the yellow one, but as you can see, you do not have a very good constraining power from this, just because you don't have enough simulations to directly train the estimator. And on the other hand, here I'm also showing what you have with 10,000 high-fidelity particle simulations. So this is so the posterior field is close to what you have if you just do this calibrated particle simulations. But this will be much more expensive than the yellow one. And so here is a more quantitative description of the evaluation of the of whether these estimates are biased. So here I'm showing you the empirical coverage, which means that, for example, if you look at the 0.6, 60%, this will tell you whether there is really 60% of the truth within your 60% credible region. So ideally, you will want to have a diagonal curve for this, which means that your posterior is perfectly calibrated. And so as you can see, all the solid lines, these are the calibrated posterior, this have a diagonal coverage curve. But on the other hand, if you do not do the calibration, this can be biased either because you do not have enough simulation, which is the case for the green, or because if your simulation used for training is not accurate enough, which is the case for the red and yellow. And so this is a quantitative measurement of the constraining power from all the different training sets and different data compression schemes. So I want to say that all the posteriors here are calibrated to have a diagonal empirical coverage curve. So this is a real so in this sense, this is a fair comparison between these estimators. So for the constraining power, I'm measuring the inverse volume of the 1 sigma region of this three-dimensional posterior. So if this quantity is large, this means that you will have good constraining power. And so first of all, if you compare, for example, the different data compression schemes, I found that the convolutional neural network always outperform the other predefined summary statistics, even in the low simulation budget limits. And on the other hand, if you compare the particle match with this transfer function fraction, which is the star, you will find that you will get almost the same constraining power as you directly train with a lot of particle simulations. So you will get the same constraining power, but this will be much cheaper. Okay, so let me summarize this talk. So in this talk, I introduced a new framework for the simulation-based inference, which can be applied to any SQL problem that you find that the high-fidelity simulations are too expensive to run. So I want to advocate that, because I mean, if you do not do this calibration, then whether we can use this approximate simulator is just a binary yes or no. So it just depends on your error tolerance, whether you think this level of error is fine. But if you do the calibration, then the posterior is guaranteed to be unbiased on the high-fidelity simulator. So in this sense, this posterior is always usable. It's just that how optimal it is depends on the accuracy of your training set. And for the particular cosmology problem, we just use a very simple particle match simulation with the transfer function fraction, which works well as the quantitative resolution. But if we have a better emulator, if you have a better approximate simulator, then this can work at even smaller scales. Okay, so for the next step, I want to run, because I mean in this work I just show that this can work with this 1 gigaparsec box simulations. But to really analyze the current data, we will need a much larger box size than this. So for the next step, I want to run a mega quixote simulation, which is roughly 10 times the quixote setup. But I want to do this with particle match, so that is doable given the limit of the constraint of our computational resources. And once we have this, we can, for example, analyze the Galaxy over density maps with just one single simulation box. So we do not need to stack in multiple small blocks to get the large cosmological volume. And also I would say in this talk I did nothing for the virality effect. I'm just doing the documentary over density map. So in practice, we will also need to do something for the virality effect, which I will leave for future work. So for example, I think the first step is to to train this method with different verification model like the HOD model, and then I will check whether this is unbiased on the real hydrodynamic simulations. So this will be the future work. And the code is available on GitHub, but since I'm busy with the applications, so I don't have the chance to add the document. So I will do this after I have a postdoc offer. Okay, so I'm writing down the talk. Thanks. I have to take any questions.
Question?
Hi, yeah, I thought this was really interesting.
Mhm.
So on your slide, like one before, yeah, here, sorry.
This one?
The next one, sorry, you said optimality matters, depends on simulator accuracy. And I think that question is really interesting because technically you could quantify that, right? Like your simulator accuracy is like the number of particles you're using or like the size of like a pixel, right? And like if you use less particles or your resolution is worse, then your simulator is going to be like less accurate depending on the perfect simulation, right?
Yes.
And so then, could you do something where you like quantify how many quantiles you need to approximate the true like distribution as a function of like number of particles or particle size? Because presumably like as the approximator becomes more approximate, then you need to work harder to calibrate based on that.
So
That makes sense?
are you asking the number of the number of quantiles estimated by this neural network?
Yeah, like.
I would say that's not, I mean, as long as your posterior is not that ugly, so you currently if your posterior looks good as something like this, so you can always just do like 15 or 20 quantiles, and then you can just do the interpolation to get the full distribution. You do not need more quantiles than this.
Okay.
So I think this depends more on the shape of your posterior instead of like the simulation accuracy.
Sure, so what do you think would change if your like approximations become more approximate? What do you think would change?
So, I mean that, so if you have an accurate simulator, then in this panel you will find that it's not that bad.
Yeah.
If the simulation is not accurate, then in this panel it's very bad. And so there will be some kind of information loss during the calibration, which explains why if you go to larger kmax, I mean, this is not slightly worse than if you have a lot of paleo simulation. And so the technique is, so I mean, technically, if the if all of your posterior is biased by the same amount, then the calibration will recover the perfect posterior. But if there's, because if I average over the error over the calibration data set, but if it's not, if this is not the case, you will lose some information. And so so if we go back to the question, I mean, if the simulation is more accurate, then you will almost recover the full constraining power. If it's not, then you will lose a little bit of information, but it's still unbiased, so it's still usable.
Okay, yeah, I guess I was wondering like, how bad can your approximation be and how does that still work? But like,
For that, you can look at the particle mesh only without correction. So this is really fast at 1.5 of kmax, but you can say you will still get some information from this. This is even better than if you do the particle mesh with the 10,000 particle. So if you do the pulse spectrum with the 10,000 particle simulations.
All right, one more here. Yeah, anyone?
Let's see someone else.
Before we give the mic to the most senior person.
Yes, right. You should not let the most senior people ask the question. So on one of your early slides, you had X going through an embedding on the way to the neural net. And if you are talking about 128 megaparticles and you aspire to go to 128 gigaparticles, right, that's a huge amount of input for a neural net. So the choice of that embedding, right, where that yellow box is an optional embedding. One slide. Yeah, that one. So it seems like the choice of that embedding is very important. or?
So I'm using the convolutional neural network for this part. Yes, sorry, I don't get the question, so what's the question?
Okay, so you're putting that through a CNN and then taking the outputs of that as the input to the MLP.
Yes,
And how do you make sure that that CNN is outputting something that expresses the information in the density field? I mean, I don't know, you're just starting with a huge amount of data and it seems like you have to boil it down to something. Are you doing this on the 3D density distribution or 2D
that's
slices?
2D, but I think this will also work on 3D, it's just that 2D is
Oh,
faster.
you're only doing 2D right now, okay, that's much easier, okay.
Yeah.
Okay.
Interesting point as to what sort of network is better to summarize a huge amount of input.
Yeah, because if that embedding isn't right, then nothing else will work, so like, it's really important that, yeah.
All right, any other questions? I think both speakers are here for at least the rest of today and perhaps even tomorrow. At least in your case, so there's a schedule if you want to have more detailed discussions with them. Other than that, thank you so much for the talks to both of you. Let's thank you again.